f for f of m in terms of the first derivative plus 1/2 the quadratic covariation integral of the second derivative. And I've written here the notation for the Frechet derivative, the kth Frechet derivative in terms of directional derivatives. Okay, to motivate the free version, the main results of the talk, I'll talk about an application of this classical Ito's formula to M being an n by n matrix valued process, and F being the map you get from functional calculus of a C2 scalar function. And the end game, as I told you, will be the n equals infinity version of the resultant formula, i.e. the free Ito formula. Okay, to start talking about what kinds of processes M will be concerned with, I'm going to fix a little n tuple of independent n by n, big N by n, Hermitian matrix Brownian motion. I'll be a little bit more concrete about this in just a second. So concretely, we're going to take this appropriately rescaled Hilbert-Schmidt inner product, and notice that this is a real inner product on the space of Hermitian matrices, n by n Hermitian matrices. And we're going to let E be an orthonormal basis for this real vector space of Hermitian n by n matrices. Then xi, where xi is the Brownian motion up here, that's going to be expressed in terms of the orthonormal basis as BIE here, and the element of the orthonormal basis. Here, this collection, BIE, is a collection of independent real valued Brownian motions. So that's an easier way to state what it means to have an n tuple of matrix valued Brownian motions. And then notice again, we have little n indices for the number of Brownian motions. And then the space of Hermitian matrices is a real n squared dimensional vector space. So we have n times n squared of these Brownian motions. And I'll fix this capital X1 through Xn throughout the talk. There'll always be Hermitian Brownian motions. Okay, now I'll tell you what kinds of processes M I will discuss in the talk. A matrix valued process M is going to be called an n by n matrix Ito process if you can write it as the starting point, and then a Brownian stochastic integral piece, and then a regular old bounded variation integral piece. Now, this notation right here bears some explanation. I told you before when we started that we're allowed to integrate processes with values in linear maps. So here, you should view this as the stochastic integral against this Brownian motion of the process, the linear map valued process that at time t takes a matrix C and returns AIT C BIT. So it's this multiplying on the left and right process. By the way, I should mention that the actual results apply to more general kinds of matrix valued processes, but to simplify the notation, I'll restrict to these kind of more simple looking processes. So for the rest of the talk, when I say matrix Ito process, I will mean something like this. So what we're going to do for the motivation, essentially, although the formula is kind of independent interest, is we're going to apply Ito's formula that I stated before to f of m, where m is a Hermitian n by n matrix Ito process, and f is a scalar function of a real variable that is C2. So now I'm going to discuss matrix functional calculus in a way that will be most suggestive of the kind of infinite dimensional free case. All right, so here we go, Hermitian matrix functional calculus. Recall that if M is a Hermitian matrix, then the linear algebra spectral theorem says that M is unitarily diagonalizable. Now, my favorite way to conceptualize unitary diagonalizability is in terms of a spectral resolution, which is also what you use in the infinite dimensional case. But I'll set some notation for the finite dimensional version here. So equivalently, we can say that M is expressible as this sum, or decomposable as this sum over the eigenvalues lambda of M of lambda times P lambda M, where P lambda M is the orthogonal projection onto the lambda eigenspace of M. So that's my favorite way to view orthogonal diagonalizability. You can prove that that is equivalent. This, as I said, was called the spectral resolution of M, and it allows us to give a definition of functional calculus. So if you have a function f of the eigenvalues with complex, it takes values in the complex numbers, you can define f of this matrix to be the sum over the eigenvalues of f of the eigenvalue times the spectral projection associated with that eigenvalue. Okay, and then the last thing I'll do is, this was just a function of the eigenvalues, but if you have a function of where you can plug in any real number, you can turn it into a function that takes in a Hermitian matrix and returns the matrix f of that Hermitian matrix. So I will use for a real function, a function of a real variable f, I will write f sub mnc for the map associated, or the associated map that you get by using functional calculus. M maps to f of n. All right. So one thing that we'll need to know about this matrix functional calculus is what the derivatives of this map are, assuming that this map has some smoothness. And that's actually a little bit of a delicate game to play, differentiating matrix functional calculus, or more generally operator functional calculus. I will show you what the formulas look like in the cases of a C1 function and a C2 function, because that's what we will need for the Ito formula. So first I'll set some notation. If you have a C1 function f, I'm going to write f bracket 1 for the two variable function that's given by this difference quotient when lambda is not equal to mu, and then it's given by f prime of lambda when lambda equals mu. This is called the first divided difference of the function f. In free probability language, you would call it the non-commutative derivative, or the free difference quotient of f. And there's a higher order version for a C2 function, and it's basically this f bracket 2, the second divided difference of the function f, and it's defined basically as the first non-commutative derivative of the first non-commutative derivative. And so you recursively define it this way in terms of the the f1. And then again, you have to take the limit as n goes, mu goes to nu to get the definition for mu equals nu. But if f is C2, then that limit will exist. All right, so these will be the functions that show up in the formulas for the derivatives of matrix functional calculus that I will state now. So this theorem was basically proven by Daletsky and Crane in 1956. And it says that if k is a natural number and f is a ck scalar function, then the associated matrix functional calculus is also a ck map from Hermitian matrices to n by n matrices. And there's a formula in the general case, but I'll just state the formula for the relevant situation for us. So that's k is in 1 and 2. K equals 1 and k equals 2. So the first derivative of the matrix functional calculus at m in the direction of b is going to be this sum, this double sum over the eigenvalues involving the first divided difference. One thing that I would like to point out is that from the definition that I gave of matrix functional calculus, what looks like is going on is that you take this function of two variables, two real variables, you act the first variable on the left of the input b, and then you act the second variable on the right of the input b. So that's an observation that will be relevant to us later in our interpretation of the infinite dimensional case. For the second derivative, it's similar, except we have more variables. Again, we have this three variable function, and it looks like we're, well, first of all, we're symmetrizing in the entries b1 and b2. That's a generic phenomenon when you take fresh A derivatives. But it looks like we're taking this function of three variables, acting the first variable on the left of the input, the second variable in the middle of the two inputs, and then the last variable all the way on the outside at the end to the right. So these are the formulas for the first and second derivatives of functional calculus, at least in the matrix case. I'll pause just for a second so you can study the formula a little more if you'd like. Okay. So now I will state the formula in the matrix case, and I'll just say that this matrix formula that I'm about to state will follow by applying general Ito's formula with the derivative formulas that I just showed you, and also the quadratic covariation rules that look like this in this matrix case. Recall that x1 through xn, little n, are independent Hermitian matrix Brownian motions, and you can show by well-known quadratic covariation rules for real valued Brownian motions that the matrix case takes this form. And I won't say too much more about that, but it is what's going to explain the appearance of the normalized trace that shows up in the formula that I'll show you. So here we go. This is what I call the functional Ito formula. And the term functional here is meant to refer to functional calculus for matrices. So it says that if M is a Hermitian n by n matrix Ito process, so that's why I have, instead of a BIT here, I have an AIT star, so that if you take the star of that stochastic integral, you will flip it and still get the same thing if you apply the star here, because remember, xi is Hermitian Brownian motion. And then, of course, I said it's supposed to be Hermitian, so we should also have that K is a Hermitian matrix value process. All right, so if we have such an Ito process and a C2 function, then you can give an expression for the functional calculus F applied to MT. And the formula for the first derivative piece, we get this guy, this same double sum over the eigenvalues of this divided difference, PLMT, stochastically integrated against DMT, and then P mu MT on the side. Then we'll get the Ito correction term, and it's a little bit too long to write out on the same line, so I'll call it CIT for correction term, the ith correction term. And it is expressible this way. Again, this comes from that triple sum that we saw for the second derivative, and also these quadratic covariation rules. That's how this trace comes up. So we get 2 times the second divided difference of F, and then A, we trace out the middle, AI star P mu M AI, and then AI star P nu M at the end. Now, this is written in the literature as delta sub AI tensor AI star of M. We won't say too much about that, but that is again supposed to suggest that there are more general kinds of stochastic integrands that you can consider, and you would notate for those more general integrands, you would notate this correction term by putting the integrand in the subscript. But anyway, this is the functional Ito formula for matrices. Again, I'll pause on the formula a little bit so you can look at it.
Can I just ask a super quick question? So,
Yeah.
Philippe Bian had this paper back in, I don't know, mid-90s.
Yep.
About how different is this result from the things that he was considered?
Yeah, actually, that's going to be, we're going to get to that actually.
Okay.
This is this paper, and then some other applications of the formula were the motivation for this study, but I'll address that in detail.
Thanks.
Yeah, for sure. Thank you. Okay, so thankfully, we're going to transition to the free situation now. And thankfully, I get to assume that people are familiar with free probability now. I don't usually get that luxury in the talks I give, so that's good. I will just list a dictionary that we'll use to transition from the matrix case to the, or the classical case to the free case. So let's have omega FP be a probability space. As usual, we're going to replace bounded random variables and expectation, or matrix valued random variables and expectation of trace with a tracial von Neumann algebra A tau, or I like to call it a W star probability space, A tau. We're going to replace independence with free independence. We're going to replace a classical notion of distribution with non-commutative or star distribution. And then the universal distribution in this free world, instead of being the normal distribution, it'll be the semicircle distribution. And when we have variance t, we should have variance t here. That's what I'll write for sigma t for the semicircle distribution. And then slightly less obvious, but if you think about it for a little bit, it makes sense. If you have a filtration of your probability space, which we need to do stochastic calculus for adaptedness, we're going to replace that with an increasing collection indexed by R plus of von Neumann subalgebras of the underlying W star probability space. And then finally, we're going to replace our adapted stochastic processes M with maps from R plus to the von Neumann algebra M, such that at time t, the map lands in the teeth element of the filtration. And as practice, we'll transition our definition of Brownian motion to this free setting. So we're going to fix a filtered W star probability space, AT tau, and an adapted self-adjoint process is going to be called a free, or I usually like to say semicircular Brownian motion, if it x of 0 is 0, and whenever s is less than t, xt minus xs is freely independent from as. That's the free increment assumption, and it has non-commutative distribution semicircle of variance t minus s. So that's going to be the definition of free or semicircular Brownian motion. Okay, so as you might already know or might not be surprised to hear, if you have an n tuple, little x1 through little xn, of freely independent semicircular Brownian motions, then this n tuple will be, as a process, will be the large n limit of our Hermitian Brownian motion n tuple in some appropriate sense. So we should expect free analogs of constructions or results involving the xi's, the Hermitian Brownian motions. So in particular, Philippe Bion and Roland Speicher in 1998, they developed a theory of free stochastic integration against semicircular Brownian motion that allows one to make sense of these free stochastic integrals. For example, when A, B, and C are continuous adapted processes. And those formulas that I gave you at the beginning of the talk that hand-wavily define the regular classical stochastic integral, loosely speaking, those are the same formulas that define the free stochastic integral in this setting. Okay, so we're going to take for granted that such stochastic integrals make sense to us per the work of Bion and Speicher. So in analogy with the matrix case, we're going to talk, instead of matrix Ito processes, we're going to talk about free Ito processes. And that's going to be a process M that satisfies this equation where we have a starting point, a free stochastic integral piece, and a regular old integral piece. And once again, the same comment applies. You can formulate such a definition for much more general integrands, not just these AI, DXI, BI terms, but more general biprocesses, if you've heard of this stuff before. But again, for simplicity, I'll stick with these easy to write down free Ito processes. All right, just like in the matrix case, we're going to state a free Ito formula for f of m, where f is a scalar function. And then since xi infinity equals little xi, this is going to be the n equals infinity analog of the functional Ito formula. So in the infinite dimensional case, instead of having these projections onto the eigenvalues, onto the eigenspaces, you have what's called a projection valued spectral measure. And loosely speaking, you replace this definition as a sum. In the infinite dimensional case, you define functional calculus as this integral. So if we just naively reinterpret the quantities from the formula, what we get is this double sum should be a double integral. And this triple sum should be a triple integral. And then we should replace little traces with taus. That's the way, from our dictionary, that's the way we should be doing these things. Now, this seems fine and dandy, but actually, if you're familiar with projection valued measure theory, you're only allowed to integrate scalar functions against projection valued measures. And if you just look at this, for example, well, maybe we'll take this one. This is a scalar function, so we can make sense of this integral, the innermost one. And even this is just a complex measure, so we can still integrate that. But then you get to this third variable, and what you're trying to do is integrate an operator valued function against a projection valued measure, and you're not usually allowed to do that. And actually, this is the precise problem that an object called a multiple operator integral was invented to solve. And I won't go into the rigorous definition of multiple operator integrals, but suffice it to say that these quantities that I just wrote down, they can be made sense of most of the time. So I'll state a little bit of a pseudo theorem about that. But first, I'll recall that in the matrix case, f was a C2 function. So what we're aiming for is making sense of these integrals for f as close to C2 as possible. And the pseudo theorem is that there is a rather large class of C2 functions called non-commutative C2 functions, for which those formal integrals do make sense. And the part of the theorem is that, for example, C2 functions with locally Holder continuous second derivative lie in this class. The takeaway is that if f is just a little bit better than C2, one can make sense of such things using these multiple operator integrals. But for the sake of time, I won't rigorously define them. I'm happy to do so perhaps at the end of the talk or in separate discussions. This brings us to the formula of interest, which is a reinterpretation of that matrix formula, or not a reinterpretation, an analog of that matrix formula in the free case. So it says if you have a self-adjoint free Ito process and a non-commutative C2 function, you get this expression in terms of these multiple operator integrals, which is exactly the interpretation we built toward. And now I'm just on time, or just barely before time. I'll give a few remarks that address Dima's question, and then we can then I'll take your questions as well. So first, this formula on the previous slide is actually a generalization of a formula that Bian and Speicher proved in their original 1998 paper. First of all, they only worked with one semicircular Brownian motion, so they worked with the n=1 case. Secondly, and perhaps more interestingly, is they considered these functions f that can be expressed as a Fourier transform of a complex measure with a finite second moment. And part of the results that I proved are that functions of this form, actually even more generally, functions that are on each compact interval representable as a Fourier transform of a complex measure with two finite moments. These are non-commutative C2 functions, so they lie in this class, but they are a strict subset of NC2, and that's not trivial. You have to construct a counterexample, but that can be done. And then finally, the quantities in the Ito formula that Bian and Speicher proved, they were not stated in terms of this object called a multiple operator integral. They were explicit formulas involving this measure mu of the functions they considered. All right, that's about all I had to say for you. Thank you for your attention, and I'd be happy to take your questions.